Again, my name is Shawn Domagal-Goldman. My affiliation just changed. I am on a detail to NASA headquarters from NASA's Goddard Space Flight Center with a new title and a new hat, which is to be the program scientist for the Great Observatories Maturation Program. It's our way of making sure that we've got a strategy to do things in a way that makes future flagship missions be done in a way that's going to keep them more likely to be on schedule and budget. The first of those is the Habitable Worlds Observatory, which is going to be the subject of what I'll be talking to all of you about today, in the title of this talk, which is How Lonely or Not is the Universe? And I thought Sasha did a wonderful job setting up this question, because I completely agree with him. We have to think about a world in which we search for signs of life beyond Earth and beyond our solar system, but we come up with a null result. And we want to make sure, especially for our largest investments, and I want to be clear, I'm not against the fishing expedition science. Wonderful science is done that way. But for our largest investments, we have to make sure that in a null result case, we still learn something fundamental about the universe that we live in. And we've got a history of learning about the universe. I think about the Drake equation a lot because I think it was, to be honest, prescient of the science that we were going to do and the advances that we made and the ways that we do astronomy from professionals all the way to amateurs has been honestly predicted by the Drake equation. Because if you think about what we've done over time, we have a much better understanding today of the formation rate of stars in the galaxy and of the fraction of stars with planetary systems. And recently we've gotten data on the number of planets that could harbor life per planetary system. These numbers were supposed to be things that would eventually lead into an estimate of the number of technologically advanced civilizations in our galaxy. But they've also been kind of, if you look back retrospectively, a history of where we've gone so far as a field in astrophysics. And I think they've not only been a history, they've been a way that, as I said, changed the way we do astronomy, not just with space-based telescopes, not just with large ground-based facilities, but I could walk outside with my kid and talk to her about the night sky in ways that I couldn't have talked about it when I was a kid going out with my parents. And when I was a kid, we'd go out, we'd count the stars. You look at the night sky and say, how many stars can you see? I lived in Chicago. There's a lot of light pollution. You couldn't see many. Now I live in DC. And actually tonight, I can't see any at all because of the haze that's over us right now from the Canadian wildfires. But if there was a clear sky, I could go outside with my daughter and not just count stars, but I could count planets, because I know that for every star, on average, there's a planet around the star. And I also know that on average, for every 10 planets or so, every 10 or so stars that we count, there's about one planet out there as well that could harbor global biospheres. And those are fundamentally different things. We had no knowledge of this when I was a child. Just in my lifetime, that's changed the way we literally look at the night sky. We count the stars differently than we did 20 years ago. And what we want to do is we want to get to a place where 20 years from now, we revolutionize the way we count the stars in the night sky again, where we're not just counting stars, we're not just counting potentially habitable worlds, and frankly, we're not even counting worlds that harbor life. We want to get at a point where we can point at a star in the sky and say around that star there is a planet that has signs that a global biosphere exists on that world. That's the goal. That's where we're trying to get to. And if we do that enough, as Sasha pointed out, whether we succeed or fail in finding that biosphere around another star, we'll be able to say something profound, which is how common are such worlds? If we don't find any at all, we can at least say they're around less than 10% of the stars in our solar neighborhood. And if we do have a positive detection or multiple positive detections, we'll be able to estimate on the fraction of planets that do harbor biospheres out of the number that could. And we're basically moving one step further in the Drake equation. And I think that's just amazing. I mean, we didn't draw it up that way. We didn't look and say, like, here's the Drake equation, what's the next step? But it has continued to be, and if we do HWO and are successful with it, it will continue to be prescient in predicting the history of science and astrophysics. Now, how are we going to do that? You've heard a lot about this from the other, by the way, just wonderful speakers. It is both wonderful and intimidating to come after people that have explained this science and the technical challenges so well. We're going to do that by capturing that picture of the pale blue dot. And as poetic as it is, that all the things that have ever happened on this world have happened on that one pixel of light, That's really challenging scientifically to say, well, does that pixel of light have a biosphere? And as others have stated, the way we're going to do that assessment is to not rely on the spatial dimension, but to rely on the spectral dimension, to spread the light out into a spectrum, analyze that spectrum for markers of gases in the atmosphere that would be indicative of massive biological activity, not something seeping out in a small scale like we would search for life in the solar system to find, but something that's, I would say, pervasively inhabited, something where the signal is so large we can pick it out against the background of the star after we've blocked out the starlight from the star in a spectrum of that world. And you've heard a lot from the other speakers about planet diversity, and I think that's extremely important, and in fact it expands to the diversity of Earth, even our own planet. Even if I'm sitting inside the box of looking for Earth-like life, and I'm not thinking about the things that we don't know about, Earth has had more than one biosphere in its history. On the left here, you'll see what is really a geology diagram. It is a reconstruction of the gases in Earth's atmosphere over time, with time going back as you march up the figure. And these are the biosignature gases: oxygen, ozone, also habitability gases like carbon dioxide and water, and methane, which is another biosignature gas. This is Earth's modern day spectrum, where you might look for signs for some of those gases in the spectrum as it exists today on Earth. But if you went back 500 million years, just 10% of the history of the Earth, you would have seen a different spectrum. You would have seen one without the features from oxygen, but for which the ozone features would still be there. That tells us that looking for that ozone signature is going to extend the history of Earth that we could detect life for back not just 500 million years, but 2.5 billion years. Now, if you go back further to that 2.5 billion year marker, you go to a wildly different environment. And I'm fond of saying that Archean Earth, the period on Earth before the rise of oxygen in the atmosphere, had a different atmospheric chemistry, had a different ecosystem globally. It literally had caused the rocks on Earth to be of a different color. The rocks we dig up today from that time period are colored differently because the Earth was so dramatically different at the time. It is, in my opinion, well, actually, I think this is an opinion, but I think it's one strongly based in fact. Archean Earth is the most alien biosphere for which we currently have data. We have to go back in time because we don't have that evidence of a biosphere beyond Earth yet to find something that is foreign from what our current expectations are. And if you go back in time, or if you look to Earth back in time, the spectrum would look like this. And we have two here because it depends. There are times in Earth's history we think there was a shrouding haze, like I talked about being over my head in DC today. We think there was a global haze made of organic molecules, similar to what existed on Titan. And in the context of an atmosphere with carbon dioxide and water, as we had on Archean Earth, that haze would have only been sustainable if you had a massive production of methane. That's only possible if you have a biosphere operating and creating that methane at the surface. Even if you didn't have the haze, you could detect the methane coming out of that biosphere and look for that as a biosignature. And I say all of this because the Habitable Worlds Observatory is based on the legacy of the LUVOIR and HABEX mission concept studies, which you heard about earlier. And both of those studies, and HWO as a result, were designed in a way to not just be able to detect the kinds of life that we have on Earth today, but the alien biospheres that we have not just knowledge of occurring in the past on Earth, but data in the form of the rock record we have of what those biospheres were like. These are proof of concept biospheres that are different from today, but we know existed and operated in the past. And so we're going to design the telescope to have a wavelength range so that it can characterize the biospheres we know have existed on Earth throughout its whole inhabited history. That goes out to the ultraviolet to detect things like ozone and hazes, and it goes out into the infrared to calculate things relevant to the planet's climate. We won't measure the temperature directly, as Sasha talked about. You need to go out in the mid-infrared for that. You can detect some of the gases related to climate and habitability. Now, in terms of our target list, we are looking nearby. We're looking at a variety of stars. This is a plot of the distance that we would search, that we would conduct the search on, and the different star types we would conduct it on, and how complete, basically, if there was a habitable zone planet, what is the likelihood we could detect it, is sort of the color diagram on this. And you can see this is mostly FGK, sun-like stars, but there are a few A-type stars we would look at, as well as a handful of Ms. And they extend out to the nearest 20-ish to 25 parsecs from our sun. Now, some of these are very familiar to us, especially if you're a nerd like me and you are a sci-fi fan, because the closest stars are the ones you could point at in the sky and name. They're also the ones that pop up in our science fiction literature and movies and TV shows. And this is an example from the HabEx report of where some of our targets are near and dear to our hearts because we've read about them in those literature or watched them in the movies. Now, to make sure we found a true biosphere, not just nature mimicking one through photochemical or astrophysical processes, we need some other characteristics for the telescope. It has to have ultraviolet wavelength coverage so that we can measure the masses of the planets and help ensure that they are truly habitable worlds. We also need to characterize the host stars themselves because we need the ultraviolet light well understood, because that's going to be a major driver of photochemical processes that could otherwise mimic biospheres. And we also need to have the orbits of these worlds imaged multiple times, planets imaged multiple times over the course of their orbits, so we know their orbits very well. We're going to have all this. We're going to make sure that there's the instrumentation to do the UV spectroscopy and overall have the right context of that planet, not just to find potential biospheres, but the goal is to also rule out all of the known non-biological processes that could create the same signals that we think are coming from biology. Now, I want to be honest here. If some postdoc or grad student or someone does not come out with a paper finding some other inventive way to make those signals a month or a year or a couple of years after our announced discovery, I'll honestly be disappointed. That's where I think multiple missions like LIFE and HWO in whatever order they occur could eventually be incredibly important, because that's where you enter the scientific method, right? You would have a detection, an alternate explanation, and you'd have a predicted observation that would resolve the debate between whether that was from biology or not. That's a scientific process. And if you take nothing else from this series of talks today, I hope you take away that we're at a turning point in our history where we're not just speculating about how lonely the universe is. We're talking about building specific things that will go and apply the scientific method, conduct specific scientific experiments to do that. And that's not a one-off. That's the start of a process. And we're at that turning point, and that's incredibly exciting. Now, HWO, it's a flagship mission for the Astrophysics Division at NASA, which means it can't just do one science case. We have to serve the broad astrophysics community, and I'm going to just step quickly through some of the science cases that we're anticipating. Some of those are very close to home. Literally, we're going to be looking at higher resolution at solar system small bodies like Ceres. We're also going to be looking at potentially habitable worlds inside our solar system, like Europa. We're going to be able to image the surface of that world in high detail and image the plumes in high resolution that are coming out from that subsurface ocean and monitor that cryovolcanism over time. We're going to put this search for life in a context of the cosmos that gave birth to the planets that could harbor life by having a spatial resolution that can resolve individual stars. And through that, understand the dark matter properties of the universe that this life could exist within. And lastly, but I think this is perhaps the most important part, is we also need to make space for the inventiveness and the genius of humans that maybe haven't even been born yet today, and certainly don't even have their PhDs or undergraduate degrees yet. And think of the questions that they will have and will know to ask with the telescope that's not going to launch for a while that we can't even imagine today. This is the Hubble Deep Field. This came out of someone taking Hubble and saying, I'm going to point that at the darkest part of the sky, and I'm just going to find out what's there. And the expectation was nothing would be there. And the reality was this, a sea of galaxies. So if you build a massive telescope and you let brilliant people do cool things with it, they will do things you did not imagine would be possible. And we want to imagine that too. Now, this is the technical challenge. The technical challenge is shown on this diagram. You probably can't see it. It is a pale blue dot. It's hiding somewhere. You can't see it because of all the white on the diagram is literally overwhelming your detectors. Even if I darken that and I get rid of that bright light, it still is hard to see. And I'm going to point it out just in case it's right here. I don't know if you can see it in the room or not. I can barely see it on my screen. And this highlights the two challenges for HWO. To see something this faint, you need a huge telescope. You need a big light bucket, especially if you want to do it on a survey looking at things far, far away. And you need to block out the starlight, because even if you have that big light bucket, your detectors are just going to be overwhelmed. And this leads to a system between the telescope and the instruments on the back end that need to operate in sync and darn near perfectly and better than anything else we've ever built. This is one concept image of what a telescope like that could look like. This is one of many options. So this isn't like how it's going to look. This is like where we're at today. It's a snapshot. Think of it that way. By the way, this barrel thing that you see on the front, that's to protect us from the micrometeorites that we've been experiencing with JWST at L2. We know that's a problem. We're already incorporating the lessons we've learned from JWST technologically, programmatically, scientifically into our thinking of HWL. And we're going to have that telescope to work with the coronagraph. You heard this earlier from Becky, is it needs to be incredibly stable to the levels of picometers, 10 picometer level stability over 10 minutes. How are we going to do that? Through design, control, and tolerance. We're going to design it to be stable. We're going to have multiple segments. Each segment's going to be very stable, and we're going to be able to verify the stability of those in the lab. We already can measure with precision the level of stability that we need from a performance standpoint. We're going to control those segments. Both segment to segment, we're going to have little pistons that if they feel a vibration, they're going to push back and keep the vibration from going too far and actually stabilize it, actively control each segment. We're also going to have the telescope potentially have its own system to separate it from the spacecraft bus, where there's all kinds of motors and gyros and things going on that could lead the vibrations up in the telescope. So what you're hearing is we're going to have multiple levels of control. The mirror segments are going to be stable. They are going to be controlled. The mirror itself is going to be separated from some of the noisy stuff on the spacecraft bus. And on top of that, well, this is a diagram. It's an overview of sort of all the layers of stability, including the deformable mirrors and the coronagraph. And if we do all that, when we do all that well, we have a lot of technological progress being made, both by government and by our industry partners. If we do all that, we're going to start to get to this point where we can have tolerance, which is how do we look at the image on the back end? And this figure here, I'll tell you, it's already outdated. And it's going to soon be, the stuff we got today is even going to be outdated by a longer shot soon, because we have post-processing algorithms that people have been developing for a while. And the thing that's coming down the pipe real quick is we're looking at AI approaches to this, where you could have an AI looking at the back end image coming out of the system and do the speckle reduction algorithms in place of the things that we're using today. All of these areas have been dramatically advanced over the last, well, honestly, 10 years. 10 years ago, people thought that this kind of activity from space would have been impossible with a segmented mirror. And it's possible. We've got a technology development plan that we have confidence can get us there. It's going to be hard and it's going to be difficult, but if we do, we're going to end up with an image like this. And the exciting thing for me is that we're not going to end up with one. We're going to end up with multiple. Our goal is to have 25 images of systems that could have habitable planets in orbit around their stars. We're going to be able to look for signs of life on those worlds. We're going to put that in the context of their host stars and the other planets in their solar system. We're going to put that in the context of our solar system and in the context of the cosmos in which all these solar systems exist. And when we do that, we're not going to have just this image on a PowerPoint slide. We're going to have this image on the front page of newspapers all over the world and on buildings and on some of our largest cities. And that's the moment I'm looking forward to, because that's the moment where, for me, the search for life and the question of how lonely is our part of the universe is no longer something that we're speculating about. It's no longer something that we've got a PowerPoint slide talking about what might happen one day. That's the moment when the image I showed in the last slide is on a building like this. That's the moment where we turn this search into something that the scientific method is engaged in. And that's the moment I'm ready to work the rest of my life for. Thank you. And I'll take questions with the rest of the panel.